All right, let's talk about units for pressure. We mentioned a few of them already. In particular, we started talking about atmospheres, and we really didn't know what to do with that. I just kind of said what's kind of like the average amount of pressure at sea level. But really, anytime you've got there's kind of two approaches to coming up with pressure units. The first one is anytime you have a force unit and an area unit, you can combine them to make a new pressure unit. So the one that was brought up the other day was pounds per square inch, which in science we don't usually write as PSI. We write it as pounds over inches squared. That's the scientific way of writing PSI, right? What could we use? What would we use if we were trying to do this in metric units? Kilometers. Square meters, good. What is our force unit for metric units? Close, that's a mass unit. And force originally comes from definition, looks like this, where force is equal to a mass times an acceleration. If you plug in the acceleration due to gravity and you plug in the imperial unit for mass, does anybody know what the imperial unit for mass is? Give you a hint, it's not pounds. Nope, that's metric. Slugs. Slugs times acceleration due to gravity gives you pounds. We're not going to mess with that though. So mass, if we're going to plug in metric units, the mass we'll plug in will be in kilograms. And what are acceleration units? Meters per second is, say that again? Meters per second, because acceleration is the change in velocity per time. So if velocity in metric units is meters per second, the change in velocity is meters per second, which we write as meters per second squared. So if our mass is in kilograms and our acceleration is in meters per second squared, which if we're talking about the acceleration due to gravity on Earth, we have a standard value for that. Does anybody know what the acceleration due to gravity on Earth is? 9.81. So lowercase a, we got to just differentiate here. We have to be careful because capital A is area. Lowercase a is acceleration. So acceleration due to gravity is 9.81 meters per second squared. Do you actually have that show up in another class? Or you just read the procedure? Physics. Good. So if we're not on Earth, we're not using this acceleration. This is the big distinction between mass and force, is that mass doesn't change based on what planet you're on. The kilograms that something weighs or the slugs that something has as its mass is independent of gravity. However, what we actually measure when we put something on a scale is actually the force of gravity on that object. So force in imperial units is pounds. Force in metric units is kilograms times meters over second squared, which is a mouthful. It doesn't really make a whole lot of sense. So we redefine these as kilograms times meters over second squared is defined as a Newton. After the Newton. Isaac Newton. Right? So the shorthand, the abbreviation is just a capital N. So how is this valuable to us? Well, now we have the metric force unit. And what is our metric area unit going to be? So it's not inches squared, meters squared. Newtons per meter squared has its own name as well. It's not PSI. Call that a Pascal, after Blaise Pascal, the mathematician and physicist who first defined some of these terms. All right, so how did you measure your objects yesterday when you put them on top of the syringe? We measured the compression, but we also measured so that's the volume, right? We looked at what is the volume of the gas by reading the side of the syringe. We also had to measure the kilograms or the grams of the object, right? So you probably have a spreadsheet or your data at least that looks like mass in grams, and then you have 5 data points, right? And then you measured the volume. And what units did you use on volume? Cubic centimeters. cc's, cubic centimeters, which is another word for milliliters. Basically, we're not actually going to do a whole lot of math with the volume. So we can kind of use whatever units we want as long as we're consistent. The trick is going to be getting our pressure to make sense. Because remember, what's our goal? What are we trying to plot with this lab? A graph of what axes, though? All of them. Pressure and volume. That was the second one we did. Volume. So our final goal is going to be to plot. We'll put pressure on the x-axis and volume on the y. So we need to find our total pressure. How are we going to do that from just mass of an object? Volume's easy, so we'll leave volume alone. How do we get from mass to pressure? Well, can we get from mass to force? I just erased it, but we have a calculation for that, right? Force on the object is going to be mass times acceleration due to gravity. That's our measured number. And A is 9.81 meters per second squared. So what units do we need our mass to be in? We measured it in grams, but if we want this to come out as newtons, it was kilograms. Right, we're splitting hairs a little bit, but basically physicists do everything in kilograms and meters. Chemists pretty much always do everything in grams and centimeters because we just work on a smaller scale. But anytime you're using a physics equation like this, or like pressure equals force over area, you want to put it in physics units to make everything work out. So we're going to want to put on your spreadsheets for your calculations here, we're going to want to put another column. We're going to want mass in kilograms. That's easy to conversion to do though, right? We know how to do that one by this point. Once we get our mass in kilograms, what's the next column going to be? We're trying to get to pressure inside of our container, right? Inside of our syringe. We're going to need area at some point, but is the area changing? I mean, the total surface area is changing a little bit, but really we're adding force just to one little part of that syringe, right? Just the plunger that moves up and down. So we're going to call the area a constant. We're going to say that the area is just the area of the plunger. So we are going to need that at some point. We'll write that on a list of things over here. We're going to need area of the plunger. And what units are we going to want that to be in? So pressure is force over an area. If we're talking about the area here, we want to put it in metric units. We actually want it to be in the area to be in square meters. So you get a really small number, right? Because that little circle is not a whole square meter, right? The TV here is like a square meter. We're going to be much smaller than that. So we're going to want this to be in meters squared. What do we need the force to be in? Newtons, so that we can get newtons per square meter. So what's our next column here? What are we going to do with all of our masses in kilograms? I'm just struggling today. We do the mass, not times area, the other A. Acceleration. So we'll make a column that's force in newtons. So if we're filling in our calculations here, if we know our mass in grams, I'll fill in. Let's call this A3. Let's say our calculation to get etc. Our calculation to get our mass in kilograms, just divide by 1,000, right? What's our calculation then to get force in newtons? Times 9.81. So A, B, C. See, who needs spreadsheets when you can just make a spreadsheet on the whiteboard, right? Just make spreadsheet paper. I think they call that an Excel sheet. All right. Is that enough? Does that get us to our final pressure inside? So far, all we have is the force that we added by putting a textbook on top, right? If we want to turn that into the pressure added, what do we need to do? Divide by the area. So back over here, that's going to be a constant for all of our data points. So whatever you calculate your area as, we're just going to say, okay, our pressure in pascals, and really that's pressure added, because there was already some pressure in there. We'll talk about that in a second. But our units are then going to be pascals. Right, and so your lab write-up had you calculate this area separately, right? The trick part with it is that you just need to make sure it's in square meters, not square centimeters. So if you initially calculated your area in square centimeters, you have to do a conversion.
Pressure units, because we were told to note down the atmospheric pressure on the day that we can.
Yes, you were.
Is our final answer going to be atmospheric?
We're gonna have to do something to make all of those make sense, right? Because the pressure that we added, we put it in pascals because we had to go through all these other calculations to get there. But we don't measure atmospheric pressure in pascals. So there's going to have to be one. That's why I specified pressure added.
Okay.
Pressure total is going to be one more column. So pressure total is going to be your added pressure plus the atmospheric pressure. right? Because there was already some pressure inside the syringe. So anybody know what units he wrote down for the atmospheric pressure? That was the number. Oh, it was, you give it to him in,
ATM.
oh, you're kinder than I am. We actually measure atmospheric pressure in a unit called torr, T-O-R-R. And torr is actually an abbreviation for millimeters of mercury. Has anybody ever heard the phrase the mercury is rising or mercury is falling? What does it mean? You would think that because we used to use mercury in thermometers, right? It actually is barometric pressure. Because the first way we figured out how to measure atmospheric pressure was actually using a mercury barometer. And a mercury barometer is basically it's like a test tube that's filled with mercury and then stood up on its end. So basically you take this test tube and you submerge it in a pool of mercury. Mercury is a liquid at room temperature, so you let this tube fill up with mercury, and then you take it and you stand it up. What happens if you took a test tube and you filled it with water, and then you stood it up and water stays in the tube, right? It's like putting your thumb over the top of a straw and then pulling the straw out. The water stays in the straw, right? Why is that? The force of gravity is pushing on that liquid, is pulling that liquid down. It's not capillary action. It's not surface tension either. It's actually atmospheric pressure. When we tilt this up and it's filled with mercury, what happens if the mercury comes down? What happens to that empty space up here? What is it? Is it air? It was empty, or it was completely filled with mercury. We tipped it up, and then if the mercury came down, there's nothing in there. It's actually a vacuum. Never actually sure how to spell vacuum. Seems like there should be 2 C's, but there's actually 2 U's, I think. Or is there just 2 N's? 2 V's. Go 2 V's. That makes sense. So
It's 2 U's, you're right.
it's 2 U's. So this works with a straw when you pull a straw out of your drink and it stays in there, because if the liquid fell out, started falling down, you'd be creating a vacuum. But there's actually constantly air molecules bouncing off of the surface here. Those air molecules are pushing down on the surface of the liquid and kind of forcing it to up into the tubes, to stay up into the tube. So basically, you only actually get this vacuum when the force of gravity on the mercury is equal to the force, the atmospheric pressure pushing down on the surface of the liquid. So the way we originally measured barometric pressure was we literally just measured the height of the mercury where it stopped rising. Because there's a point where the weight of the mercury is equal to the atmospheric pressure, and then if you extend the tube further upward, the mercury stays at the same height. You can do the same thing with water. If you actually took a tube of water, say a garden hose, and you filled it with water and then you capped off one end and raised that tube up while you kept the other end in a tub of water, one force of gravity is equal to the force of the atmospheric pressure pushing on the surface of the water will stop rising. Until then, the water stays in there and it won't create a vacuum until you get above a certain height. We don't use water for barometers though, because it turns out you'd have to make the tube really, really long for that to work. You can make a water barometer, but it has to be about 30 feet tall. So we use mercury because it's a liquid and it's about 13 times more dense than water. So for mercury, you only have to go about, if you're at sea level, it's about 760 millimeters above the surface of the mercury. Still a fairly long ways, but not nearly as much as 30 feet. Plus, mercury doesn't really evaporate very well. And if you use water for this, you actually do get a little bit of water vapor up at the top as well, which throws off your answers because then we created some molecules where there's not supposed to be any molecules. So we use mercury for several reasons. It's really dense, relatively easy to find and cheap to make, and it has a really, really low vapor pressure. So basically we can treat that like it's a true vacuum. So all that to say, when your height of your mercury starts rising and falling, that's where the phrase the mercury is rising comes from. Mercury rising, mercury falling has to do with the barometric pressure. Because what happens to the barometric pressure when we have a storm coming in? It drops. Most partly because, and that's part of what causes all the wind that we get up here at the top of the mountains. We get a lot of wind when we have weather coming in, right? If we have a really low pressure system in one part of the map, say in Carson Valley, and we have high pressure next to it, there's naturally a movement of those air molecules to try and even out that pressure that causes wind. So when you have low pressure, it causes wind to blow in, and that brings with it weather systems usually.
Are we low pressure in this case, or the higher pressure?
So when we have if it's a low pressure system, it means the storm's coming.
Okay.
Once the storm gets here, it tends to even out a little bit. And then a high pressure system basically means nothing is coming towards us. All of our air is moving towards other places. So high pressure is always good weather, clear weather anyway.
Yeah.
Low pressure system, if the storm's not here, it's on its way. And so why does that matter for us? Well, it means that our total pressure inside of our system, inside of our syringes, is based on not just the pressure we added, but also the pressure that was originally there. And the pressure that was originally there, you were given it in atmospheres, but we actually have a mercury barometer at the college. So we actually measure this directly. You literally just measure what height the mercury stops at. It just stays there attached to the wall, and you just take a measurement. And so it was, yesterday it was 604.24, which is the same thing as saying millimeters of mercury. If you look up a meteorology app or website and want to look at what the barometric pressure is, because we're in the US and we can't do anything the easy way, it's in inches of mercury. So you can actually take inches of mercury and turn it into millimeters of mercury just by doing a regular length conversion. So basically, this is a third way of measuring pressure. So the first two ways of measuring pressure were based on force units divided by area. And then there was atmospheres that was basically, we're just going to call this the standard. We're going to say sea level on average is 1 atmosphere. The other way to do it is by physically measuring a property like height of mercury. So they're all tied together. There's actually different instances where we'd want to use different cases. Like for instance, if I literally have a mercury barometer, why wouldn't we just measure the height as our unit? That's actually a really simple way to do that. It's really easy to calibrate too. You literally take a ruler and you set it next to the tube, and you can measure your pressure in millimeters of mercury. So the standard atmospheric pressure in millimeters of mercury is 760 torr. And again, torr and millimeters of mercury, literally the same thing. They just changed the name after after the guy who first figured this out died, they changed the units to honor him. So this is Torr is short for Torricelli, the Italian physicist who first figured out how to make a mercury barometer. So 760 torr is equal to exactly 1 atmosphere, which is also equal to 14.1 psi. And that's a measured number, which is also equal to 101,325 pascals. So go ahead, Diego.
How much about the per inches of mercury here in the United States?
It's 30 something.
Okay.
I'd have to look it up because I don't actually do anything in inches of mercury if I can help it. But just take 760 millimeters and convert it to inches. It winds up being a little under 3 feet. We're not at atmospheric pressure. We're up here in the mountains, right? So our standard atmospheric pressure is not 760 torr or 1 atmosphere. It's usually actually about 610 torr. It was really windy yesterday. We had weather coming in, right? So yesterday, our atmospheric pressure was 604.2 torr. So it was a little bit low yesterday. So if you don't take that into account, that'll actually throw off your answers a little bit. So what does that mean as far as finding our total pressure inside here? Well, if we're going to add our total our pressure added to our atmospheric pressure, they have to be the same units. Turns out it doesn't actually matter which pressure units you use, you just have to do it consistently. So you can either take atmospheric pressure and convert it to pascals. You can take pascals and convert it to atmospheres or convert it to torr. As long as they're the same pressure units, it doesn't matter. Right? So since you were given atmospheric pressure in atmospheres, what was it? If all of these are equal to each other, that means we can make any combination of these into a conversion factor, right? So we can convert straight from pascals to torr if we want, because we can say 101,325 pascals equals 760 torr. That's a conversion factor, right? So it's pretty straightforward to convert different pressure units because they're always all related to 1 atmosphere. They're always all equal to the same thing. Anybody think of any other pressure units?
This is pressure, but on some buildings they have like a rating for how much snow can like. I'm not sure.
So that is a pressure because it's a force over an area, except that they then normalize by the usual density of snow to say that you can have 3 feet of snow per square foot or something along those lines, right?
Yeah.
So that's related to, although usually you can just go, if it's more than 3 feet, it's a problem. But it really is a pressure unit because it's pounds over a square foot or something along those lines. The other one that shows up is called a bar, BAR, which is short for barometric pressure. 1 bar is really close to 1 atmosphere. A bar is just pascals divided by 100,000. So 1 atmosphere is 1.01325 bar. Then there's also like hectopascals, which is like I believe it's like a kilopascal, if I'm remembering. No. 1,000 hectopascals is equal to 1 bar. So it's like 100 pascals is a hectopascal or something like that. That shows up sometimes especially in meteorology, not really in science classrooms though. for the most part, these are the 5 most common units. And when in doubt in chemistry, put everything in atmospheres. You put everything in atmospheres, you won't go wrong. So what is our atmospheric pressure in pascals? Since we have our pressure added in pascals, we only have to do 1 conversion if we just put our atmospheric pressure in pascals. How do we get there? 0.795 atmospheres and 1 atmosphere. It's 100,000 pascals. 101,325 pascals. So we get something around 80,000, right?
80,553 change.
Which that's a measured number, so we only get to keep 3 sig figs out of it. So 8.06 times 10 to the 4 pascals. How many? Does anybody run any of the numbers on your data from yesterday yet? Yeah, makes sense. But figure, let's call it one of those textbooks was a kilogram, just to make the math easy. So we're going to say 1 kilogram times 9.81. So we're at 9 newtons. Call it 10 newtons. Divided by the area, which, if I'm remembering right, usually winds up something like 0.01 square meters. So we're at 10 newtons divided by 0.01 is the same as 10 divided by. So multiply by 100 instead of divide by 100. 1,000. So we're going to we added about 1,000, something in the ballpark of 1,000 for each of your data points. We started with 80,000. So basically we didn't add that much pressure to the system by weighing those books. Even if you managed to weigh 10 kilograms of books on top of the syringe, which would be a lot, you're still only looking at, so 10 kilograms would then give us something like 90,000 pascals total. Yeah.
Then obviously another bond, but what?
We haven't done anything with volume yet because we're trying to plot pressure versus volume. So we didn't actually need to do anything with volume yet. You can put CCs in there though. Just keep track of our units. Once you get to total pressure, which is going to be our pressure added plus 8.06 10 to the 4, give it our total pressure in pascals. Once we get our total pressure, now we can make our chart. And because our original goal was to make this graph, and I hopefully have it look something like a 1/x graph. That's what we expect based on our understanding of how pressure and volume work, right? We did those thought experiments the other day, and I can do a better job with this. It's an asymptote, right? Because we can't get down to 0 pressure no matter how big we make the volume. Realistically though, because everything that you measured, what was the heaviest, who had the heaviest object that you managed to put on top of your syringe yesterday? What was the heaviest mass that anybody measured that you got to balance? So 1.10 to the 4 grams, which is what in kilograms? Yeah, about 13 kilograms. Everything you added was between 0 and 13 kilograms. We're pretty much everything that you measured is going to be in that little section right there. we didn't really get to any extreme measures, right? Because at most, with 13 kilograms, your pressure added is going to be something in the ballpark of 1,300 pascals. And if you're starting from 80,000 pascals, that's not that large of a jump, right? We didn't manage to get a full doubling of the pressure or anything like that, right? So your data, when you plot it, is actually just going to be, it's going to look like a straight line. Close to a straight line. So how do we know if we can't see any of the extremes? How do we know if it's a straight line or if it's a 1 over x?
Can we use our amount of pressure with 0 weight on top of it?
That can be one of our data points, but that's still just going to be in the same basic area, right? If this is, call that 80,000, actually call that data point 80,000. Everything else is going to be right in that same area. Anybody have any ideas? We could do a trend line for this to see if it matches. It's still going to look pretty linear though. So we're going to use a science technique, data analysis technique. Basically, all the math for making trend lines works best if you're doing linear data. Who's taking stats here? Do you have to do a line of best fit by hand once? Maybe once, but then you use your calculator for it after that, right? Because it's such a nasty equation. It's even worse if you have to do it for like a parabola or a 1 over x. And the math behind it isn't as real. Stats is all, if you ask mathematicians, they already don't count stats as real math. And it's even less so if you start trying to do lines of best fit for more complicated functions. So basically, we only want to do a line of best fit for something that's actually linear. So with that in mind, if we're expecting it to be a 1 over x graph, what we can actually do is we can plot, I'll leave this one here. We can plot pressure versus 1 over volume, which doesn't really make any sense. I remember not liking this as a student the first time I saw it. What do you mean I can just do 1 over volume? 1 over volume doesn't mean anything. It's useless. What units is it going to be? It's going to be an inverse cubic centimeters. Those units don't even make any sense. How can we do this? We can do this because mathematically, this should give us a straight line. So even if we only get a small section of our data points, when we do 1 over volume, they're still all going to be pretty tightly gathered here, but we can do a line of best fit for that. And if we do a line of best fit here and compare it to a line of best fit here, it'll be a better match here. Even though this looks linear, if we're really careful taking our data, this will actually give us a better R squared value. Because R squared is our measure for how good our line of best fit is, right? Our trend line. Trend lines are better if R squared is closer to what? Closer to 1. So we might get an R squared value of 0.985 or something here. Over here, this still looks linear, but our R squared value might be like 0.922. Still pretty linear, but not as good as this. So this is our end goal, is actually the last step we're going to do. The only calculation we're going to do with the volume is after you make this graph, you're going to add a column. And it's just going to be 1 over volume. And the units are going to be 1 over cubic centimeters. 1 over volume doesn't make any sense, but it allows us to get a straight line when we plot it. All right, this is going to wind up being a relatively common thing in the sciences where we say, well, we've got this complicated mathematical relationship between these variables we can measure. But I'm gonna just do some algebra to it to make it look like y equals mx plus b. And then if you plot the right variables against each other, you get a straight line. So, for instance, if you look at, we can use vapor pressure. If you look at vapor pressure of water versus temperature, you get this kind of, this weird sort of function that kind of looks like this. This does not match with anything that you've seen in algebra yet. Does anybody know a function that looks anything like that? It's not even a true logarithmic function because it has this weird little piece down here. It turns out vapor pressure is equal to E to the minus delta H of vaporization, which we know what that number is, right? Does anybody remember what that was? What units was delta H in? Even if you don't remember what it was called. It was the energy term, right? This is the energy of vaporization. Enthalpy is what we call that. Over RT, where R is a constant and T is temperature in Kelvin. That's not a very fun function to try and make linear. But if you solve for it, if you rearrange it a little bit, we can get natural log of vapor pressure is equal to minus delta H over R times 1 over T plus a constant. With that in mind, we can actually get a straight line out of this. If you plot natural log of vapor pressure versus 1 over temperature, then the slope of that line winds up being delta H over this constant. And you get a y-intercept that doesn't really mean anything. But we can get a straight line, which means we can get a trend line for it. So I'm just putting this up there as an example of where you see this in other places in sciences. This idea that as long as we can make it look like y equals mx plus b, we can get a straight line if we plot the right variables. And there's a lot of functions that look complicated that if we get creative with some algebra, we can make them look like y equals mx plus b. We don't need to go that far for this one. We just want to plot 1 over volume on our y and pressure on our x. And if we did everything right and we measured our numbers properly, we should get a nice clean straight line there. All right. That was a lot. We have about 20 minutes left. Should we try and do some of the calculations? Try and make these charts? And then you can finish up with that tomorrow. All right. So I'll come around and answer questions. If you have spreadsheet questions, need any help remembering any of the many things we just talked about. Yeah. I think I put the deadline as Thursday. But you're getting the lab isn't? Okay, I can fix that. We'll make it due Friday just to give you the extra day.